Hi, and welcome back to EOS Friday. Last week we took a look at the bounds of the Rachford-Rice equation, and this time we want to try to actually solve the Rachford-Rice equation without having to actually go in and visually find the root here. The way we're going to try to solve it is by three different approaches. It's going to be using a bisection method, an unbounded Newton search, and a bounded Newton search. We're also going to take a look at how picking our initial value affects the solution, and also what is the radius of convergence with the Newton method. Jumping straight into it, let's take a look at the bisection solution. So we have our initial guess right here, which we can move around. And the idea of the bisection search is that we pick the midpoint between this point here and our bound. We pick the midpoint and we see, is that value greater than 0 or less than 0? And we know that our right bound is going to have a negative value and our left point here has a positive value. When our midpoint has a positive value as well, we know our solution has to be to the right of that. Repeating this process again, we get this value, then this value, then this value, and then finally we get very close to the solution. What happens if we change our initial guess? Nothing really much. We get kind of close to the solution no matter how we do it. That's one of the advantages of the bisection method. However, if we take our initial guess and put it very close to our solution, then what you see is that it takes a long step to the left, going further away from our solution, and then it iterates itself back in. This is one of the disadvantages of the bisection search. Moving on to the unbounded Newton search. The idea here is that we take and find the slope at the initial guess, see where this slope crosses the 0 value, and then we use that as the basis for our new guess, shown here. Repeating the same process, we get this. So after 5 iterations, we were very close to the solution. Let's see how this changes as we change the initial guess. Seems like a pretty good solution, right? Okay, so what happens if we get a bit funkier Rachford-Rice equation? Let's say we increase the light component very close to 1. And what you see is that our unbounded Newton search is going to go find the next step, and then it's going to shoot past our bound and continue diverging outside of the solution space. This is the biggest downside of the unbounded Newton search, and this is why we want to bound it. Continuing with the same troublesome example, let's try to use the bounded Newton search instead. We take our tangent, say that it's inside the bound, therefore we choose the point, go up, and start our next iteration. However, in the second iteration, we find our tangent, we find where the tangent crosses 0, and we see that that's outside of the bound, shown here with the black marker. So we do a bisection search instead, and pick the midpoint between the first iteration and the estimate of the second iteration, shown here as a cross. We then go up, we see that this is a new value, and then we calculate the tangent again. And as you see, it's also going to shoot off outside of the bound here, so we pick the midpoint again. And we're basically just doing a bisection search. Repeating this process 2 more times, we get this. So you see here on the 5th iteration, we don't overshoot the bounds. So we go back to our very efficient Newton solver. So let's see if we can break this as well. Well, if we continue to increase here, kind of going off, you see we're always converging to the solution. We never overshoot. And if we go to the right of the solution, we converge very quickly. If we take a look at our original example, you see that we also get the same convergence as an unbounded Newton search. So it's clear that the Newton method is a very efficient way of solving the Rachford-Rice equation. Therefore, we should talk a little bit about when the Newton method will converge. The criteria for the Newton method to get an estimate closer to 0 than where you currently are is having the function times the second derivative of the function being greater than 0. So if we plot that here, that product here, what you'll see is that the product of the function with its double derivative is greater than 0 on the left here and on the right. And in this green zone here, what you'll see is that if you pick any value in here, your solution with the Newton method is always going to get to a smaller and smaller value. And therefore, it's always going to converge within this region. Whereas on the left here, it's going to get closer and closer until you get to this point, and then it's going to deviate more and more until you get to the solution again. This is a very powerful tool to check if your solution is going to converge or not. Finally, we move the initial guess around a bit, but since we're only looking at a binary system, there's actually a special case here where choosing the midpoint gives you the exact solution. Don't trust me? Well, let's try. So I've set the initial guess to be the midpoint between the left and the right asymptote here. If we put the bounded Newton search on again, you'll see, boom. After the first guess, we go straight to the solution and converge there. You might say, well, that's only a special case for this set of k values, Marcus, you're cheating. Well, let's try to change the k values. See, every now and then it gets some numerical weird stuff happening, but you can actually go in and do the algebra, and you'll see that this is actually always the case. So for this week, we also have a Excel file that does the same as this decimals file. So if you want to go into the details, you can get into that. And for next week, we're going to see what are the main issues when solving the Rachford-Rice equation in an actual Flash solver. And with that, I'd just like to say thanks for watching.